Welcome to the seminar. Ralf is student in data science and he wants to predict battery health state with a simple machine learning algorithm.
So let's go to Riga to find out more. Once we arrived in Riga, we were warmly welcomed by our hosts and counterparts at Riga Technical University, one of our EUT Plus partner universities. They gave us a comprehensive tour of the RTU campus, with the highlight being the RTU High Performance Computing Center. This is Latvia's largest high-performance computing provider, and they need to be able to operate even when the power shuts down and there's a blackout. For that purpose, they've installed a wall of massive batteries which keep the HPC running until the generator kicks in. These massive batteries are able to sustain power for about 40 minutes. However, it is paramount for the HPC to know how healthy their batteries are and when they need to start replacing them. But what does health of a battery actually mean? Batteries degrade over time with each charge and discharge cycle. This degradation, however, can vary between them depending on manufacturing defects. So some batteries last as the manufacturer intended, and some of them degrade much more rapidly. And now we try to define the state of health of a battery as the current capacity, which we find here. So we have state of health is equal to the current capacity divided by the nominal capacity we have at the start. And then we just multiply this by 100% to get a nice value. So why don't we just straight up measure the state of health? You could use a method called Coulomb counting, but that would mean having to fully discharge your battery with a constant rate in a supervised and controlled environment. This introduces operational downtime and incurs stress on the battery by adding another charge and discharge cycle. Some purposes cannot allow this type of operational downtime. The backup batteries at RTU's High Performance Computing Center need to be operational at all times in case of a power outage, at least until the generator kicks in. The same goes for implantable medical devices. You cannot have any operational downtime, because your patient depends on the device, but you absolutely do need to know how healthy the battery is. Knowledge about when to recharge and when to replace is paramount. That's why we want to explore a data-driven method to predict the battery state of health. But what data do we actually already have? We have a charging log that gives us the current and voltage at distinct times. But if we have 100 measurements each second, the size and dimension of the dataset rises quickly. So let's use domain knowledge to significantly reduce the number of features considered. Lithium-ion batteries charge in two distinct steps. First, there's the constant current charge, in which the voltage starts somewhat low, increases relatively quickly at the start, and then rises slowly until the voltage maximum threshold is reached. Meanwhile, the current I stays constant. This phase typically makes up the bulk of the charging. In the second phase, the voltage stays constant at its maximum value and the current is falling. If we were to always charge from 0% to 100%, this would already be enough information. We just calculated constant current and constant voltage charge capacities. This can be done by just taking the integrals over the respective time frames. And especially for the constant current charge, this is relatively simple because the current is, as the name implies, constant. We just have to multiply the current with the time interval from the time we stopped charging with constant current to the time we started charging it. However, especially for implanted medical devices, we never want to reach a 0% empty state. We want the devices to still function and we want them to have some backup battery left. So instead, we also look at the initial charge voltage, as well as the final charge voltage and the final current of the charge. These give us information about the state of the battery at the start and at the end of charging. We've established the necessary knowledge about the characteristics and data of batteries. Now I want to introduce to you the simple machine learning algorithm we're going to use. K nearest neighbor. The K simply stands for any natural number. We've talked a lot about charging, so allow me to introduce it to you with an example about charging your head and liver with some additional poison. Right here we see a graph of white and red wines. They are graphed on their levels of rutin and myricity. Both of those are flavor compounds. In order to apply K nearest neighbor, we have to know which is which already in our training data set, because K nearest neighbor is a supervised learning method. That means it learns from labeled data. Now, if we were to add another wine in here, but we wouldn't yet know which one it was, and it just turned out to be here, we would probably guess that it's a red wine. And so would K nearest neighbor, because the core assumption behind it is locality. That means similar data points tend to be close to each other. Now, if however we were to introduce another glass of wine, and it's right here, and we just look at the one nearest neighbor, we might think this is a red wine. But when we look closer, we might also think there's a lot more white wine around there. So that is just here to demonstrate that the number we choose for K matters. The number we choose for K means how many neighbors in the area do we look at, and then decide by a majority vote which it is. So if we were to say, example, we look at the 5 nearest neighbor of this glass, then we would get 1 red wine and 4 white wines, and the 4 white wines outvote the red one. So we would predict this as being a white wine, which might hopefully coincide with our intuitive assumption. Now, what makes K nearest neighbor a little bit unique is that it is a lazy learner. Lazy learner means there is no computational training step. You simply compare the labeled data with your input. That's it. And that makes it feasible to compute even on devices like implanted medical devices, as long as they can store the data. Now let's circle back to our battery characteristics. There are just 2 steps left that we need to take before we can apply some version of K nearest neighbor. First of those steps is to normalize the features, because they're on different scales and we want them to be on the same interval so that in a sense they become comparable. But then again, by normalizing them, they all somewhat hold equal weight. That might not reflect reality, so with either methods like particle swarm optimization or with domain knowledge, we may allocate weights to different features if we might say that the initial voltage is less important than another metric maybe. And with those weights, we then want to calculate the Euclidean distances between the points. That's all we need to do. We store those and we're good to apply K nearest neighbor regression. The difference here to the previous example with the wine is we no longer have distinct categorization. Instead, we have some kind of averaging to predict based on what the neighbor said. So once again, depending on how many neighbors we choose, our prediction based on the constant current charge capacity depends. 1 is too hyperlocal, 2 is just about right in this case, 3 is chosen too broadly. But in reality, this green function is unknown to us, so choosing K is not trivial, and it always depends on your case. If we take all 5 features into account as previously discussed, we will of course get better results. Thank you for your attention, and fun fact of today, the Hochschule Darmstadt is starting a new bachelor in data science, so if you like this blend of domain knowledge and mathematics, feel free to apply.